Have you ever pondered about the working of gradient descent with momentum? It's like a thrilling roller coaster ride for data in a higher dimensional space, accelerating towards the best solution. Let's dive deep into this essential concept in machine learning and data science. Imagine standing on a hilly terrain, blindfolded, tasked with finding the lowest point. You probably feel the ground beneath your feet, identify the direction of steepest descent, and take a step in that direction. That's what gradient descent does. But what if, while moving ahead, you come across a point that feels like a lowest point, but it is just a valley above the lowest point in the entire mountain range? This point is called as local minima. Gradient descent with momentum helps us get past this local minima and achieve the optimal solution. It is an ingenious method that combines the concept of momentum from physics and gradient descent, enabling faster convergence and mitigating the problem of local minima by using the momentum from previous step to reach faster towards your goal. Mathematically, the update rule for gradient descent is given by the formula where theta t represents parameter value at time step t, theta t minus represents parameter value at time step t minus 1. This represents gradient of loss function with respect to parameter value at t minus 1, and alpha represents the learning rate. The negative sign ensures that we move in the opposite direction of the gradient. Imagine you are tracking the gradient of your cost function over time, and at each iteration, you are getting a new value of gradient. Now, instead of using this raw gradient, we replace the gradient with exponential average to compute a smoother estimate of our gradient's trend. This exponential average is called as momentum. Let's dive deep into the workings of momentum. We start with an initial estimate m0, which is generally set to 0. Then at each time step, we update our estimate by using our current gradient and previous estimate. We blend these two values using an exponential factor beta, and the final formula looks like this. Now, once we calculate the momentum, the formula for gradient descent is changed from this to this, where mt represents momentum at time step t, alpha is the learning rate, beta is the momentum term, and 1 minus beta represents the weight given to the current gradient. Let's visualize how different values of beta affects the smoothing of the gradients. Let's first import the essential libraries. Now let's generate random data which will be used as an representation of gradient values. Let's seed it, say 42. Now this gradient values will be used to visualize the smoothing effect. Now over here you can see this is how our random gradient values looks like. These values are pretty noisy, and we would want a more smoother approach rather than these noises, as these noises are responsible for the gradient descent to get stuck at a local minima. Now let's create a function to compute moving averages or momentum. Now as we saw earlier, the first value for momentum is generally initialized as 0. So this is our function for momentum. Now let's define beta value. Let's start with 0. Now let's calculate our momentum. Once this momentum has been calculated, let's try to plot it. The value of momentum is almost the same as the values of gradient. This is the case because the beta values is 0. To visualize it in a more better way, let's plot both of the gradient values and momentum together. So over here, both values of original gradient and momentum are the same. But now let's try to change the value of beta. Let's change it to 0.4. So over here you can see this value is getting much more smoother. Now let's make it more smoother by keeping beta equals 0.9, and then we are getting much more smoother trend. But over here, initially the momentum takes some time to get along with the trend, but after that it smoothen out our original gradient. And if you don't want to start the momentum from 0, you can also start it from the first value of gradient. If we go that way, but then we'll get more smoother value of momentum. In a nutshell, momentum acts as a guiding light in the labyrinth of optimization. By smoothing out the erratic fluctuation in the gradient, it unveils the hidden path towards the optimal solution.